normalization works like this. So these are for each channel of the output of a convolutional network. We have channel-wise mean and standard deviation, where we divide. These are just trainable parameters. We'll ignore them for this analysis. So these means are usually calculated from the minibands. So in distributed data parallel, you have the option to either aggregate the statistics locally. So let's say we have 2 GPUs and each one sees 128 samples. You have the option to either aggregate and compute these means and standard deviation locally from 128 elements, or synchronize the statistics from 2 GPUs and aggregate the statistics to have a much better estimation of the mean and the standard deviation. Long story short, they use the synchronized version of batch normalization, while here they do another trick where they take the output of the momentum encoder, the teacher, and they shuffle its elements. And another way would be to reduce with layer normalization. I know it's like not exactly related to the actual paper or the method, but it's only if you get the small details right that you can see the effectiveness of those approaches. So it's not completely independent. Another small note for those of you who have a notion of layer normalization from sequences and transformers, I have a small slide indicating that layer normalization is different from natural language, where you have a sequence of tokens versus vision. So in convolutional neural networks, we average over when we do layer normalization, we average over the different channels and spatial dimensions and not with the batch size. While in transformers, we only average between the D model dimension, so the last dimension. So we don't average the statistics between different tokens or elements of the whole sequence. Okay, we found a way in case the batch size, we don't have the compute or the data are really large. For example, in the research center in Jülich, close to Düsseldorf, they have these huge brain scans where the experts identify that in order to learn meaningful features between those 2 brain scans, to take some crops, they cannot use 128 crops and maximize their similarity. They need to go in the level of 2000 by 2000. So there may be many use cases where you either don't have the resources or your data where you want to do representation learning are way too big. So the question is it necessary if we just optimize for performance? And the answer is no. So basically, like 1.5 years later, they made 3 tricks, basically 2 tricks. They abandoned this queue. If you want to have like the maximum possible performance on ImageNet or standard vision-based benchmarks, they abandoned this queue since they don't have like computational issues. They train with maybe 128 GPUs and the batch size of 4096. And another thing which I want you to pay attention is the symmetrization of the loss. So far, so far we have SimCLR where we have an encoder, but here, and for the next weeks, we will see that very commonly we have 2 different architectures. So this is the student and the teacher. So this is an exponential moving average, and so they are not the same network. So symmetrization doesn't make sense on SimCLR objective. But if these two models are different, then instead of feeding V1 to the student, V2 to the teacher, compute the loss, we also, since we produce the augmentation, we load the data to the GPU, we switch those values. We put V2 here, V1 here, and compute the same loss. So this is what we mean, and then we can average between these two losses. So this corresponds to this line of the code where they say symmetrized. CTR stands for cross entropy. Any questions so far? Okay. Here I will very briefly I will just illustrate some more things. I just want to show you that contrastive learning is not limited either to RGB images. So here there is another paper from these guys from MIT, where instead of playing with views of the same image, they take a scene, a multiple sensor, like a depth sensor or different views from different sensors, and maximize the mutual information between them, while considering as negatives views from other scenes. And this would result, since they create their pretext task like this would result in representations that are view invariant. Then if you have not just two views, but a set of m views, I don't know if I have here, we have how many pairs do we have for m views. So if you have a 4x4 and this is the diagonal, you have all these elements, basically the lower triangular or the upper triangular part, with m minus 1 divided by 2. So there's a number of views. When you have m views, you have m multiplied by m minus 1 divided by 2 pairs. So basically, all these would be the pairs that would be considered positives. And they take two different approaches. So they use the RGB as the reference point and take all the contrastive losses between all the other views. So this is a representation of a graph. So they represent as a graph and say, okay, we want to learn this type of connections with each loss between all those pairs. And in this case, they take all possible connections, so all possible pairs for contrastive learning. And they use usually when you have this type of problems in vision, you have a downstream task as segmentation. So these 4 rows where they created their experimental study, they vary by only the encoder weights. So they use a decoder, they train on the downstream task, but in the first they train the decoder with a random freezed encoder. Then they use this core view where they take RGB as the reference, and then they use all the possible views. And this is basically fine-tuning from random initialization where both the encoder and decoder change. And this is something that we'll cover 3 weeks from now. Basically, it's an extension from contrastive learning to multimodal. So in this case, we maximize the similarity or mutual information between images and text, so sentences. So we saw the importance of L2 normalization, why we need it, what is the difference. We saw the impact of contrastive loss and what's actually happening that features uniformly distribute themselves in the hypersphere. We saw the memory bank, that you can solve problems even where you don't have the resources, the compute power, or the problem demands you to use a small batch size, even though it's not the optimal when you just optimize for performance. But usually in real life, there are much more requirements. We saw that engineering can cause problems similar to batch normalization causing information leaks, that we should always be aware of what's happening as much as possible. And lastly, contrastive learning is not limited to RGB or single model in general images. We will cover this, the last approach, it's called CLIP, Contrastive Language Image Pre-training, in the next lectures. Any question? This is your last chance, because after we will make a small break for 10 minutes, and then we will switch to I will talk about a bit about image clustering. So any questions regarding all the contrastive, momentum encoder? Okay. Then let's make a small break. 10 minutes, okay?